Hello everyone. Now we're going to be talking about relative position. Okay. Now we know what the absolute position of two particles is. At least we have a term for it. And it's using these position vectors, where r sub a is to a from our origin, or from some sort of fixed observer, and r sub b is to our point b, also from that fixed observer. What we haven't defined is a way to talk about the position of something relative to another object. So the position of B relative to A, so where A is now being considered kind of like the origin, will be simply my position vector at B minus my position vector at A. And also notice this notation here, B divided by A. The one that's, you care about, and the one you're looking from, okay? The one you care about over the one you're looking from. So if we want to do a little example here, if we know what the position vector of B is, it's 10 and 2, 10i, 2j. And the position vector of A is, well, that's 4i and 5j. Then our position vector of B relative to A is going to be subtracting them. And similarly, my position vector of A relative to B would be doing the opposite. So it would just be the same thing, but with a different sign. So this gives us a way of talking about how things look compared to each other. And then we're going to differentiate these to figure out relative velocity. Because you've seen this before when you're on the highway and you're going, let's say 60 miles per hour. And when somebody passes you at 65 miles per hour, well, it doesn't really look like they're going 65 miles per hour, does it? No, it looks like they're going maybe 5 miles per hour. Okay, maybe 5 miles per hour. Now, in all honesty, I would have these two originating from the same point if we're doing relative velocity, but for the moment, I can't do that as easily and show it all to you. So just always come back to the whole highway example. You relative to another person is what you care about. So this is what you care about when you're on the highway. Because if somebody's going super slow and they have a very, very small, very, very large relative velocity to you, that's kind of dangerous. If you're, the granny on the highway going 20 miles per hour, and another car comes in at 120 miles per hour, 20 miles per hour here, okay. Have another car right here. Let's make it a little bit more dangerous. There we go. And he's coming in at 120 miles per hour because this guy's out of control. Well, that's a relative velocity of 100 miles per hour. That's dangerous. However, if this person's coming in at 25 miles per hour, that's a relative velocity of 5 miles per hour. That's a fender bender. Okay, that's an 18-wheeler, so fender benders are much more than that, but you get the point. So in many cases, we're going to care about relative velocity. Now, hopefully this reminds you of that whole aircraft carrier example where you have, these planes taking off, and one of them leaves and it's going 200 miles per hour. And this guy right here is going 50 miles per hour. And it says, what's the relative velocity? Well, we just subtract them. So this one, relative velocity of this compared to my aircraft carrier is 150 miles per hour. And similarly, the relative velocity of the aircraft carrier compared to my plane is 150 miles per hour, negative 150 miles per hour. If you're wondering why it's negative, it's because if you are considering yourself to be stationary, then this aircraft carrier is going to look like it's moving backwards. Okay, so let's keep on through this. But I want to mention again that it's always B minus A. It's the point that you care about minus the point you're looking from. Point you care about minus the point you're looking from. And similarly, we can figure out our velocity of B by knowing what the velocity at A is plus this relative velocity. This right here is super helpful. You're going to use it a whole bunch throughout the semester. So please, please, please don't forget these relative velocity equations. As I said earlier, they will be equal to each other, but just the negative if you switch. Okay, now relative acceleration. Now if we take the time derivative of our velocity equation, we get our acceleration equations. And so we have the absolute acceleration, and then we'll have a relative acceleration. Okay? Where with very, very similar equations, we see that the acceleration at the point we care about minus the acceleration at the point we're looking from is going to be equal to this relative acceleration. And in this case, both are accelerating, both are moving, both have a velocity. And so it's not like we're looking for the origin which doesn't move. No, we're going for something that they're both moving. And so things will change over time. And we can also have a relative acceleration, which is also going to be very, very important. These kind of equations, you're going to need to come back to these. There's going to be quite a few problems where you'll need these to solve. Places where it's pretty helpful, I'm almost certain there will be a problem where you have a box fall off of a chair that's on wheels, and you're going to have to figure out how fast that box moves at the end and how fast the wheels move at the end. So, don't forget that. I gave you a warning here. Well, that's all for this time, so thank you for listening, and I'll see you all later. Bye-bye.